Hello, everybody. In this live, what we're going to do is kind of continue where we left off last week. So last week we talked about all the various integration techniques and how to, or a lot of the integral rules, I'll say, not all of them, but most of them, and kind of how to use them. And we left off last week talking about use substitution and how that is kind of the opposite of the chain rule. What we're going to do today, let me share my screen real quick, is we're going to dive into integration by parts and talk through basically everything you need to know when it comes to integration by parts. So let's do that. So as usual, right, we're learning all the integral rules, or we're trying to understand all the integral rules. So basically, what we what we've already kind of talked about is how every rule is essentially not every rule, but like 95% of rules, everything we've learned so far is the opposite of a rule that you already know at the end of the day. So, integration by parts, what we're going to learn today, is no different, but it's just more complex, but it's the same thing. So, here, the technique, and I'll just say this again, we'll dive into the technique here, but integration by parts, that's what we're going to talk about today. That's what it's called. It is the opposite of the product rule, first and foremost. So let's explain exactly what I mean. So first off, let's start with the product rule, right? If you have like f of x times g of x, so some function f of x times another function g of x, and you take the derivative of them both, what do you really do? You take the derivative of the first one, f prime of x, right, times the f prime of x times g of x plus f of x times g prime of x. So basically, derivative of one, leave the other, plus derivative of the other, leave the one. So g prime of x. So we do that. This is the normal product rule that we all know for derivatives. And now what we're going to do is basically just use this, but take the integral of both sides. So here, I'm going to take the integral of both sides. So integral of the entire left side, and then integral of the entire right side. And then we just want to kind of simplify this and rearrange. So here, what is the integral of the derivative? Well, the derivative and integrals are opposites of one another or inverse operations. So they cancel each other out, which means we're just left with f of x times g of x, right? And then here, if I was going to simplify this, you can basically use the sum rule that we talked about a couple or last week. So you'd have the integral of f prime of x gx plus the integral of f of x times g prime of x dx, right? So if we substitute, just do that, and then what you can do is you can kind of basically just subtract this to the other side here, right? How would that go? It would basically be the same thing. So if I pull this down, all right, let me simplify that. So yeah, look, getting rid of that. So instead of an equal sign, it's just going to be a minus sign, and then that equals this thing. So this is just going to be an equal sign instead of a plus sign. So we're just literally taking this thing and subtracting it to the other side. F of x, g of x minus this whole integral. And then what I'll do is I'll just rearrange this thing. So we basically get, when we rearrange everything, we get this. And this is getting closer to what's typically given as the integration by parts formula. Again, by the way, I kind of hate the name integration by parts. I'm always complaining about how they name things. I would call it anti-product rule. That's what it is. It's the opposite of the product rule. But here, when you look at this, what we usually do as a shorthand, the way we normally write it, and I kind of hate this notation too that I'm about to write. It's just that's the textbook, or that's what's in every textbook in the U.S. basically. So we have u times dv, and that equals u. So u times v minus integral v du. Now, why would this make sense? Basically, the way to think about it is v dv is g prime of x. So, and actually, yeah, to combine this, let me do an intermediate step that will probably make more sense. This is the formula they will usually give you in a class. To be clear, they use u and dv. That's the most common. Again, I kind of hate this because these are the two letters in the alphabet that look the most the same. So it's like the most similar. Like if you try to draw a V, but you make it a little too rounded, you might think that's a U. It's like this is like a disaster waiting to happen in terms of like students getting confused like as they're writing it out for good reason. So I kind of don't like that this is the formula they write it as. But what they could have done, what I would have liked better, is if they did this: FDG equals FG minus integral DF, or I'll just say G, yeah, GDDF. I would have liked that better. So here, and hopefully you can see why this is true. So it's like basically, and again, when like F is U, G is V. When you want to look at it the normal way, F is U, G is V. But the other thing to notice is that like dg is a shorthand for g prime times dx times the differential. Why does that make sense? Here's why it makes sense. Think about the other format for the derivative of g. It would be, do you agree, dg dx, the derivative of g with respect to x, times dx, right? And then you can kind of cancel those out, and that's why you get dg. So that's why they say dg is really dg dx times dx, but dg dx, another way to write that is g prime. So it's really, again, it's like all just kind of a different notation. It all means the same thing. The bottom line is this is the key formula to use. And this is the integration by parts formula. If you've like done this in class before, this is what they probably taught you. They just probably gave you this in the textbook, and they did not tell you where it comes from. That's what I would guess. That's what usually happens. Maybe they did tell you, and that would be good if they walk through it. But basically, it's the opposite of the product rule. So what situation would this kind of help with? So let me give an example. I'm just going to come up with the simplest integration by parts problem I can think of. They usually are harder than this, but let's just say x times, there's a couple ways we could do it. Let's say cosine of x. So cosine of x. Now here, and actually, yeah, so let's say this. Now this problem that we're looking at now, you might think could be solved with u sub. So you might want to try that, right? So if you're going to set u equal to the inner function, you just like set it. Actually, let me back up a bit. If this right here was equal to 1, right, and or wasn't there at all, obviously we can just integrate that right off the bat. That's sine of x plus c. That's no problem. If this thing was x squared, then u substitution would work. Why? Because our choice of u, the inner function x squared, and again, if you don't get u sub, check out our live from last Friday. I went pretty deep into that. But basically, u equals x squared would be our value. The derivative of that is 2 times x. That is proportional to what we're multiplying by on the outside, x. So that's why it would work. But if this is just x, then it doesn't work because our choice of u here, the inner function, is like we're not like the derivative of that is a constant. So we're actually not multiplying by that, something proportional to that on the outside. So u sub fails here, I guess, is the short answer. But integration by parts works. Generally, you want to try u sub first because it's less effort. You want to give, I would say, typically give u sub 2 or 3 shots, 2 or 3 tries, minimum 2, maybe 3 or 4 if you have time. But there's a potential that like u sub, like if you try all your u subs, it fails like 3 or 4 times. And then that's when it's time to go on to integration by parts. That's usually the next one. So whenever we're multiplying two things, remember, integration by parts is the opposite of the product rule. I call it the anti-product rule. That means whenever we're multiplying two things, you should be suspicious at least that maybe integration by parts isn't the right move here. Now, as before, again, the difference is it's kind of like a step up from u sub, right? It's we don't just have to choose u anymore. We have to choose u and v, or u and dv more accurately. So it's like we have two choices to make. So we still have a similar problem that we did with u sub, and that's how to choose u. Because once you choose u, it's just whatever is left is dv. So how do you choose u? Basically, 95% of the time, this is the first rule to try. And actually, I won't write it out, but basically, u equals the thing that becomes a constant the fastest if you keep taking the derivative. And then for 2, u is the other or sometimes the only option. So that's the good news with integration by parts is there's only 2 possibilities. If this can be solved with integration by parts, you only have 2 choices. Either this thing is u and the rest is dv, or this thing is u and that are dv. Those are the only choices. So that's kind of the good news. It's like you can only be wrong. Like if integration by parts does work, it is guaranteed to work by your second choice. Like you can only be wrong once here, whereas with u sub you can be wrong 3 or 4 times. honestly, before you hit one that works. Even though that's less likely. It's not likely that you are wrong 4 times, but it does happen sometimes. So it's actually, I would argue, with integration by parts, it's actually easier to choose what you should be, but it's harder to do. That's the trade off. It's more work to do. So how do we choose this? So the thing that becomes a constant the fastest if you keep taking the derivative. So 2 options. Do we choose that or that? So if I take the derivative of cosine of x, what's that? Negative sine of x. Derivative of that, negative cosine. Derivative of that, positive sine. Derivative of that, positive cosine. Derivative of that. And then you just like get stuck in a loop. It doesn't matter how many times I take the derivative of cosine, it will never be a constant. It'll always be positive or negative sine or cosine. Always. You take the derivative a million times, it would never be a constant. With this one, though, if I take the derivative 1 time, it's a constant. Even if it was an x squared, I would still choose this because after 2 times, 2 still beats a million or never, right? So for here, this is the right choice of u. Again, this works 95% of the time, this first one. This, like 5% of the time, it fails, and then you try something, try the other option. But here, it will work. I can tell already. So basically what we do is, the way I like to do it is I like to create a little matrix here. So u is equal to x, and then dv is the rest of this stuff. And you do need to include the dx. It's not the end of the world if you don't. Like, a lot of times students forget about that. But yeah, I'll just say that. A lot of times students forget about that, but it's not a huge deal. And then du, what's du? It's just like du dx times dx. So what's du dx of this? Well, 1. So du dx is just 1. And then just multiply by dx on the other side. So just 1 times dx, basically. That's du. And then what's v here? Well, hopefully it makes sense. It's just sine of x. So you basically choose u, and then you choose dv as what's left, and then you integrate, and this is the trick. You differentiate here from u to du, you take the derivative. From dv to v, you take the integral, right? And that's why we get sine of x right there. And this is the other thing, by the way. You want to get to the point where for simple u subs, you can do them in your head. So if this was cosine of 2x, hopefully it's clear to you that that's 1/2 sine 2x, actually. You have to do the reverse of what you would think. Instead of multiplying by the derivative inside, you'd have to divide by it. But you want to get to the point where you can do those in your head, because the downside, honestly, with integration by parts is that for a lot of problems, there's literally like 3 or 4 u subs within simple u subs, right? Not the complex u subs that we talked about before, but in a typical integration by parts problem, there's often like 2 or 3 u substitutions inside of it. And you want to get to the point where you can do those in one step, like in your head, just to move faster. You don't want to get to the point where it's like you're in the middle of an integration by parts problem and you stop everything and then try to do a u sub and then put it back at the end. You don't want to get to the point where you're doing that. That's going to sabotage you. You want to get to the point where these simple u subs, and what do I mean by simple u sub? Basically, the inner function is a linear function. That's what I mean as simple, right? So like if it's like something times that, like cosine, it could be anything, like square root of whatever, but on the inside it's like something, a linear function. If it's more complicated, like x squared plus 4x, well then I'm not expecting you to do that in your head. You want to probably do real u sub with that. But for the simple ones where you have linear functions on the inside, then you want to try to do the u sub in your head. So that's good. So we did that. Hopefully that all makes sense. Now, what do we do here? This is a good time to use the formula. And again, as you're doing this, I highly recommend doing one step at a time, because it's very easy to make a single mistake. So when you look at this, let's bring this down. So we're saying that this integral, actually, when we start off, this integral, so this thing on the left, the thing we're actually trying to solve is this is u, right? This is u, this is dv. And according to we figured out what u and v would, or du and v would have to equal. So now we just kind of fill in the rest of it to the right. So how do you do that? Well, uv, so that's x times sine of x. So x times sine of x, right? Minus integral of v, what's v? Sine of x. And then what's du? 1 times dx, right? And then if you simplify this down a little bit, basically, I won't pull this down every time, but if you simplify this down a little bit, basically you have like multiplying by 1 doesn't change anything, right? So really at the end of the day, you're just taking the integral of sine of x dx. Cool. And now the question is, can you solve that? So what's the integral of sine of x? Hopefully it's clear. That's negative cosine. So it's actually minus negative cosine. So it's actually plus cosine of x. And this is kind of and then plus c, you have to remember. So, and then I'll leave this, x times sine of x, like that. So that's the idea. The answer to the original question should be that. We just solved it. And this is kind of the thing with integration by parts, by the way. Like your reward for successfully using the integration by parts formula is your present is you get another integral to solve. Integral of, in this case, it's doable, right? Like integral of sine of x, we know how to solve that by hand, but you now need to solve that integral. You now need to integrate that. And then when you do, you get what we got here. So that's good. Now, yeah, so I'll just leave it at that. But that's sometimes, and actually I'll mention this. Sometimes you could imagine, like I'll show a scenario. What if we start off with x squared? Well, then x, that would be x squared, and then we would have an x in here. That can happen. And then what do you have to do? You have to do a whole new integration by parts problem for just this thing right here. It's like you have inception. You have an integration by parts problem within another integration by parts problem. That can happen. And sometimes you need multiple, that does happen. And then sometimes you need multiple rounds of integration by parts. But here, it's a little bit more straightforward. So there you go. Now here, if you want to double check this, like if this really is the right answer, x sine of x plus cosine of x plus c, basically, if we take the derivative of that, it should equal the original thing. So here, right, because if the integral of this is that, then the derivative of this should be that. So if I take the derivative of x sine x plus cosine of x, let's see if that is actually true. Right? So if we take the derivative, or I guess also plus c. So the derivative of x sine x, the derivative of x would be 1 times sine of x, right? You would need to do the product rule here, plus x times the derivative of sine of x, which is cosine of x, right? And then what's the derivative of cosine of x? We did the product rule with just this part, plus the derivative of cosine of x, that's just minus sine of x. Derivative of c is 0. And then look at this. So we have sine of x minus sine of x. It just simplifies to x times cosine of x as the answer. That's what we started with. So we're right, in other words. That's how you can always check it. So it's like you never would have been able to, or at least I would never would have been able to, like reverse engineer this on my own. Basically, you have an answer in such a way such that you'll do the product rule of one thing and get what you actually want, and then get one thing that you don't want. And then this other thing over here is what gets rid of that. So it's really clever actually. Like the method does all this thinking for you. You don't have to worry about this. You just do, like use the method, but it finds the right product rule and the right other thing to cancel out half of the product rule. That's how it usually works out. When you do the product rule, you get one thing you don't want, and the next term cancels out. It's kind of a very clever way it works out, such that you're left with what you started with. But the bottom line is you're left with what you started with. That's the answer. So that means what we did here is correct. That is so the integral of this is that, in other words. So that's correct. Cool. So that's that. Hopefully that makes sense. That's like the general method for integration by parts. Now let's crank it up a notch. I'll do probably one more today. I think we'll probably do some other ones tomorrow because this is a more advanced technique. It's the most advanced integration technique we've talked about so far. But we'll talk about it tomorrow. What if we had like x squared here? And I already kind of mentioned what happens here. Again, it's really the same logic, right? Because like cosine of x, if we take the derivative, will never equal a constant. This will equal a constant after we do it twice. So that's still u. So u is still x squared, right? dv is still the rest of the stuff. Cosine of x dx. And then du would then be, hopefully it makes sense, 2x dx. And then v would equal sine of x. And then we do the same formula. So same formula, if I pull this down, you don't really need to worry about what's in the front. That's just whatever you start the problem with. So you can really just think of the thing on the right. So the answer equals, let's see. Actually, I will include it here. You don't really need this. Like I said, you can get rid of it. I'll keep it here, but you don't need to do that step. Because honestly, when you're doing integration by parts, you're going to need the room most of the time. So like it's very easy to run out of room on these problems. So that's why I say that. You don't generally need that. So I'm just doing that for now. But if you think about this, what's u times v? So let's go through. U is x squared, v is sine of x. So we get x squared times sine of x minus the integral of v. What's v? Sine of x times what's du? Now it's 2 times x times dx. So step one is just blindly plug everything in. Don't try to simplify initially. That you're very likely to make a mistake if you try that. So we get that. Now the next step is simplify this integral. Pull out all the constants. So I would pull out a 2. So -2 integral. I would write it like this actually. X sine of x dx. Now, what would we do here? Again, this is what I was mentioning before. This is similar to the problem we did before, but this becomes its own integration by parts problem. You need to do another round of it, basically. So we're going to have, in these brackets, it's like a whole new problem inside of these purple brackets. So again, you use the same trick. Which one becomes the derivative fastest? That's u. So x now, and then dv is the rest. So sine of x dx. V would equal, the integral of sine is actually negative cosine. The derivative of that is just 1, so du equals 1 dx. And now you do another round with that formula. So uv minus integral v du. So uv, that's x times negative cosine of x. And again, don't try to simplify yet, otherwise it's very risky. You'll make a mistake probably. And then minus, just blindly plug them in and simplify on a second step. Even though you go a little slower, it's worth it because you'll make fewer mistakes. So here, negative cosine of x, right? And then times du now, which is 1 dx. And it's a whole new problem inside these purple brackets. So what is that? To simplify this, I'm going to keep the -2 out of here for now, but this is going to be negative x cosine x. Here's now where we can simplify. Minus, so forget about the 1, pull out the minus. It's actually going to be plus the integral of positive cosine. And we now need to solve that. So we still have an integral to solve here, right? So we don't need to do another round of integration by parts because we do know how to integrate this with other techniques, just like our trig identities or trig antiderivatives, trig integrals. So this one, hopefully it's clear, that would be just sine of x plus c, right? And then we need to start backing out of this. So this, it's going to be -2, negative x cosine of x. And you got to be careful with the distributive property here. It's very easy to make one mistake. And then remember, you can't forget about this x squared we had at the top either. X squared sine x. X squared sine x. And then, again, this is not quite the full answer. So what I would do, let me grab this. So for what we have, the original, the integral of the original function is apparently x squared sine of x minus 2, distribute that, plus 2x cosine x minus 2 sine x plus c. And why is it still plus c? If I distribute the -2 to that, what's some number we don't know times -2? Well, some other number we don't know. So you could say -2c, but why not just cut out the middleman? And like c is basically means we don't know what it is. So it's like whenever you do math with arbitrary constants, it's like it just stays there. That's kind of how you can imagine that. But apparently, this is the answer. That's what we get. That is the antiderivative of this thing. And we needed 2 rounds of integration by parts, so more complicated than normal. Now here, why is this true? Or how can we check that it's true? The way we can check it, we can always do this, remember, the way we can check it is by taking the derivative. You don't have to do that. You only need to do that just if you're not sure, but if you did everything right, it should work, theoretically. So here, we need to do 2 product rules now to check this. So what's that? That's going to be 2x sine of x, so derivative of the first, leave the second, plus leave the first, derivative of the second, so cosine, right? And then, what's the second one? Again, same thing. So that's one product rule we just did. Now let's do a second product rule. So derivative of the first, 2, leave the second, 2. I'm saying 2x is the first function, by the way, here. So derivative of 2x is 2, cosine of x, and then plus, leave the first 2x times the derivative of that, which is negative sine of x. So negative 2x times sine of x, I'll say. And then what's the derivative of this? -2 cosine x. And then derivative of c is 0 for any arbitrary constant. Is this what we started with? It's not obvious yet. Let's see. So 2x sine of x. Okay, there we go. That cancels out. 2x minus 2x. 2 cosine minus 2 cosine. Actually, yes, we're just left with x squared cosine of x. That's what we started with. So that's right. That's what that means. So again, this is just an introduction to integration by parts, but you can see we're getting more complicated with our techniques. But this is one technique. This is how you do it. We'll continue with this probably tomorrow. But hopefully all of that makes sense. If you guys have any questions in the chat, remember, feel free to always just drop comments in the chat, or you can leave your comments in